What we will do, as usual, is I will, if I think that Jobb's just said something that no one will understand, mainly because I don't understand it, I'll put my hand up and wave so that he will try again. The rest of you should collect questions, and then every 20 minutes or so, I will call a break, and then we'll have a question and answer session. That sound okay?
Yeah, you can interrupt me if it's really urgent, and I will also spontaneously.
I will interrupt you with a finger, and then you decide. All right, then take it away.
Very good. So, Barry, thanks a lot for inviting me. For those who haven't met me, my name is Job Landgräbe. I make a living as an entrepreneur, but I spend half my time doing research. I'm what used to be called a Privatgelehrter, so a person who finances his own research, basically. And that has complicated reasons why I don't work for a university, but I don't want to bother with that. It has disadvantages, but it also has a lot of advantages. The main advantage is that you are not dependent on anyone. Your thinking is not constrained. Your scientific thinking is totally free, which is not totally free when you work in an academic environment. So that's the advantage, and there are many disadvantages. Anyhow, so what is the program of this course? So I think the course has become too big, but I will do as much as I can, and then maybe if I can't finish, you will get the slides, and I can maybe come another time again. But basically, I will go through the following topics. First of all, what is philosophy for physics, or philosophy of physics? Is it philosophy for physics or physics for philosophy? Then I will look with you at the metaphysical foundation of physics. So physics is basically unimaginable without Western metaphysics. And most physicists are unaware of this. I think that's a very important topic to get us started on physics. And then we will look at classical mechanics and the principle of least action, which was basically until 1950, the principle of least action, or even 1960, was totally the big idea in physics, right? So Max Planck and Richard Feynman, two of the greatest physicists of the 20th century, were both totally in love with this principle. And it has then, after 1960, been a new principle has arisen that fascinates physicists much more, but we need to look at this principle of least action as well. And we look quickly at classical mechanics, because without classical mechanics, you don't understand what's so strange about quantum mechanics. So we will not do, teaching classical mechanics takes half a year normally if you study physics, so we can only get a rough idea, but we will look a bit at it. And then we have a big segment, which is 150 slides or so, is about quantum physics. And let's see how we do this. If I can't get through it, we can also skip some of the physics. Let's see how it goes, how you enjoy it, or whether it's a pain for you. I haven't tried this before. If we can do these topics on the weekend, then we would have time for particles and ontology of physics on Monday. Particles are very fascinating, but we can't look at particles without doing quantum physics first. Okay, so this is a program for these 3 days. So here's a person I like more than Barry, but he was basically the reason why I started philosophy when I was young, because I read some of the texts by Kant. I was so fascinated by them. So Kant was a physicist, right? So he did geophysics, basically, astronomy and geophysics, and he only started doing philosophy when he was end of his 40s, and so he was teaching at the University of Königsberg. He was first teaching physics. So he came at philosophy as a physicist. And so why do we pursue philosophy of physics? So Kant wrote a big book called the Kritik der Reinen Kritik of Pure Reason, which is really focusing on this topic. How can we know something about nature? And the typical questions that we ask, that impose themselves upon us, as Kant formulates it, is as a philosopher, when physics is used for philosophy, is our will determined or free? We will not discuss this question today. It's one of the very few questions I think also Barry has discussed in his long life as a philosopher. He has dodged the question, I believe, like some other clever people. I think it's clever to dodge the question, at least in public. The second question is, does the world have an end in space? Does the world have a beginning and an end in time? These are the questions. These 3 questions are the questions from the Kant's antinum in the transcendental dialectics, in the critique of the pure reason. These are the three questions. And then the fourth question, I've added now what are the basic components of matter. It's a question that has tormented Western thought since Democritus. He was the first to think about this. So what are the basic components of matter? So these are the questions that philosophers hope to answer with the help of physics. And Kant believes that we cannot answer the first three questions in the critique or in the transcendental dialectics, so you can look it up. A3, these are 281, 22382, so these 100 pages, if you haven't read them, so this is the Akademie-Ausgabe, but even if an English translation and look for the right pages, it's always indicated the correspondence with Akademie-Ausgabe, which is a standardized edition. You don't have to copy what's on the slides. You can take, I will say a lot that's not on the slide, this you should take notes of, but don't copy the slides, it's a waste of time. Barry will give them to you, or they will be uploaded to the webpage. And so all of you should read these 100 pages. I think they're very, even if there are some mistakes in it, it's a great text for every philosopher, I think. And today it's not read enough anymore. Now, so Kant believes that you can't answer the first three questions. He had an answer to the first question, which is critique of practical reason, but the others two he believes we can't answer. I think that is still right, though our view of time and space has changed. Hi Tom, schön dich zu sehen. Our view of space and time has changed drastically. We still cannot answer them, I think, but I can't show it in this lecture because it would require me to go with you through general theory of relativity and what it means for cosmology, and that's too much for one lecture. We have too much anyhow now. Now, what the last question is concerned, what are the basic components of matter? We will see that we cannot answer it either despite the progress in physics, and that's quite depressing. So we have now, over the last 150 years, especially up until the 1970s. Since then, physics has not had this same pace anymore of progress, but until the 1970s, until quantum field theory was fully formulated out, the progress in physics was breathtaking, and despite this, we still can't answer this question. This is something I hope to show you in this course, that that basically what this slide says is that physics doesn't help us to solve the basic philosophy questions, unfortunately. Now, there's also the other way around, so that you use philosophy for physics. So that means that the scientists try to use philosophical methods to understand physics better than using only their own. And so the typical questions they're asking is, what is the scope of physics? What is the epistemology of physics? So how do physical propositions become true? How do we get to this? What is the nature of entities in physics? That's the question of the ontology, right? Which most of you who are working with Barry are working on in some way or the other. How should we interpret the results of modern physics after quantum physics and general theory of relativity? These are very important questions we will discuss in the course, and all of the people shown here had some opinion about them. And what you can see also from the slide is that in 18th and 19th century, I mean, Gauss is not depicted here. Gauss was also a great physicist, but physics was really dominated in the 17th, 18th, and 19th century by the French and the English. Then was the big age of the Germans, was in the beginning of the 20th century, for very interesting reasons. Basically because in places like Göttingen, all the mathematics has been invented. It was needed to do modern physics, and that's why the physicists there in Göttingen could make so much progress. So what is physics about? So I'm contrasting from the smallest to the largest. So this is a French synchrotron, a particle accelerator. I mean, it's just a toy model of it, but it is. You see the different circuits in which the particles can go, and then they end up here in these measurement chambers where they can collide, and the collisions can be then measured to learn something about matter. In the end, it's called high energy physics, and it's about understanding what particles are made of and how they relate to each other. Then we have here cosmology, which is the other extreme. These are the famous pillars of creation. I think the photo was taken in the 90s or early 2000s. So, and you see that these are structures of matter in the universe, and they are 4 light years long. So this is quite big. And so basically physics is about the description, explanation, and prediction of the phenomena of nature. The main topics are matter and energy, and how they interact in time and space. And the main branches are, is classical mechanics, under which falls also calorics, optics, and so on. Then because in all of these disciplines, you have also always the assumption that particles are like small balls, right? And so that when you do classical mechanics, you have small balls of particles. Then we have electromagnetism, which was a big revolution of physics in the 19th century. And then quantum physics, which arose from the beginning of the 20th century, and general theory of relativity. These are the main topics of physics. And this is now a view of what physicists, the program of physics, that has arisen since the 1970s. And so you see this is a standard model of physics, which describes it. Everything is made out of elementary particles, so this matter, we have quarks and leptons. Together, the quarks, with the help of the leptons, they can form hadrons, and hadrons, you have baryons, and then nuclei, so they are here in the baryons, these are the protons and the neutrons, they make up the atomic nucleus. Then here the electron is a lepton, so you have an electron that makes together an atom, then you have molecules. And here you have also mesons and many other particles which are not shown here. And so then we have four forces: the strong interaction, the weak interaction, the electromagnetic interaction, and the gravity. These are the four big forces that we believe today determine how matter interacts. And here you see also the carriers of the forces, so gluons, which glue together the quarks, so you can't separate the quarks. Gluons basically together, they are the effectors, carriers of the strong force. W and Z bosons are the weak force, and photons are the carriers of electromagnetism. And here they have put gravitons, of course, but we don't know about gravitons. Gravitons are just hypothetical, I've crossed them out. Then we have here quantum chromodynamics, that's the theory of how quarks are held together. And quantum electrodynamics, that's the theory of electromagnetism on a quantum scale. And also electroweak theory. These together form quantum field theory, which is the foundation of our view of matter today. We will get back to this. But to get to quantum field theory, we first need to understand basic quantum mechanics. And then we have here the electroweak theory, which was developed in the 70s and which led to a Nobel Prize. And that's very interesting because it was the first theory that could unify the weak force and electromagnetism mathematically. And because it was quite successful, it also has there's also experimental evidence for this, that the theory is at least not wrong. They thought, well, we have now managed to unify theoretically at an abstract mathematical level two of the forces. So great, now we can go about and try to unify all the four forces. So we can get a grand unified theory and then also a theory of everything. But the problem is that we don't even know what the carrier of gravitation is. Quantum gravity is a bad joke. I mean, if you go into it, it doesn't work. It has no experimental support, and also its mathematics are broken. It uses solutions of partial differential equations that are mathematically not admissible. There's a huge row going about between pure mathematicians and quantum physicists who believe in quantum gravity. I think that this is not only hypothetical, this is actually nonsensical, what they're doing. And so therefore, I don't believe at all in this grand unified theory and theory of everything. And there are also physicists who say that this can't be achieved. However, it is still very, very interesting to see the results that we get from this rectangular part, which is the part that kind of works. So this is the program of physics at a glance. And I think most physicists believe that they should try to work on this, but others also say, no, it makes no sense. So this is where we are at. This is a very high level view what the scope of physics is. So this was the first introduction part. Are there already questions? Yes.
How do we know that gluons are not hypothetical?
Oh, because we can measure them. So
They're particles?
No, they are carriers of interaction. So yes, they are particles, but they have. Let me think. So they have spin 1, and I think mass 0. But they can be measured in high energy physics experiments.
So gluons glue the strong force to the.
So they make sure that the quarks stay together to form the hadrons.
Okay, and is that okay? I won't go any further.
Yeah. So now let's look at the second part of the method. If there are no more questions, I mean this was just a soft introduction. If there are no questions, let's go to the metaphysical foundation. So physics was developed in the West, right? It's so deeply embedded in Western metaphysics, and that's very often disregarded. So if you look at textbooks, philosophy of physics textbooks, there's what is in there about the metaphysics of physics. They do metaphysics of physics themselves, but they do this by asking questions like, is there an end to the universe? What can we know about time and space? What is matter made of? What is a particle, and so on? But they don't. But there's another layer, and I want to highlight this other layer. This other layer is the following. The foundations are the following. The world is real and exclusively consists of material entities which interact via physical forces. This sentence is absolutely not uncontested. Right? That's the foundation of physics. It's a metaphysical foundation. But skepticists say, well, maybe the world is not real, so now we have a tendency to say we can ourselves define what our sexual sex is. I mean, they call it gender, but it doesn't matter. Or we can using words, we can create parts of the world. That's now very, very huge theory in philosophy. So this idea that the world is real and exclusively consists of material entities, even that, the second part, is basically for the whole antiquity, material entities were important for the Greeks, but they would not say that it exclusively consists of material entities, because there was also transcendence, the gods, the supernatural, and all of this. So this is a materialist view of the universe that is not uncontested, and which is quite special for the evolution that the West took, and basically only at the end of the 18th century, where there are philosophers who dared to say that there is no God, or beginning of the 19th century, and that all there is material, right? So this is quite new historically. The second view is that we can select systems in nature and observe entities and their relations and evolution over time and experience their real properties, so that we can experience their ontological character. And the system, just to define this for you, it's in the footnote, is, in the sense of physics, is the totality of dynamically interrelated physical elements participating in a process. And now what the physicist does, and what we do all the time, is to delimit a system. So we could say, for example, that we here, this audience and I, together form a system of a university type of encounter. And if you delimit a system, you select certain types and interactions, so types of entities and interactions, and then you also select the granularity of its elements. For example, when you think about when Galileo Galilei or Johannes Kepler or Newton thought about the solar system, they thought about the planets and the sun, and the smallest elements were the moons, right? And the moons, the planets and the sun were the smallest elements, and they thought of this, but only in terms of gravitation. So they didn't think in terms of electromagnetism. The sun is a huge source of electromagnetism. They didn't think of this. It's also a source of particles. So they didn't think of this at all, but they thought only about gravitation, and that's typical for physics. So you select a certain system in nature and think about this. Also that we can experience every properties, that we have insight into the ontological character of reality. That's also part of the second. Then the third one is that we can measure observations in natural settings. So the telescope is a very good example. Yeah, when Galileo and Kepler built their telescopes, they could start to observe entities in natural settings and then quantify aspects. So Kepler's laws, he developed them observed by astronomical observation with the telescope. Then the fourth one is that we can create hypotheses about nature of entities and their relationships, and we can, and this is basically something that started with Newton and Leibniz, formulate these in mathematical form. I mean, Kepler has also mathematical equations, but they are not as sophisticated yet. They are still based on the classical mathematics of the Greeks. And the first one, actually, to completely mathematize physics was Lagrange. He was a big genius, and he was the first one. You will see his one of his famous expression of mechanics in a while. And so this is important. We can formulate the hypothesis in mathematical form. These hypotheses are then part of theories, and we can perform experiments in which we set up natural or technical systems to perform measurements on on the systems, and these are then quantified observations in controlled environments, and the measurements are done to verify the hypothesis or to falsify them. And using induction, so this is now, even today, a very debated topic. So if we have valid experiments, we can use induction to obtain scientific knowledge. Hume denies this. Yeah. He thinks that all our physics are contingent, but he nevertheless walked over a bridge, trusted that the bridge wouldn't fall apart. And so I'm always a bit, I don't understand the anti-inductionism that is in Anglo-Saxon philosophy, but since Hume formulated his rejection of induction, it has had a very, very strong impact on Anglo-Saxon philosophy, and still today in analytic philosophies, the vast majority of analytic philosophers think that induction can't create knowledge. But most physicists do. So the physicists think that they have knowledge, and I think so too. And these are very important. These are not all the metaphysical foundations of physics, but these are the most important ones. Good morning. And before I go on, do you have any questions regarding this list? It's not complete, but it's rather illustrative, and it shows you important metaphysical assumptions of physics. Yes?
Just on the first point, it seems like something like meaning is not material, even though we can point to the correlates of like any sign or like, linguistic signifier. Like we can point to the thing that it refers to or references, but that relationship of meaning
Yes.
and how it's like occupies our consciousness, so to speak. That seems to be non-material.
Yeah,
it seems like an obvious retort.
So physicists would say that what you experience as meaning is the result of an electrochemical process. So that would be the answer of a materialistic physicist. So that all the inner experience that you have, that shows what goes on in your mind, is always a result of is basically, it is not that it is a biochemical process or electrophysiological process. So that's the answer to this. Yeah, but of course you are here pointing to the huge debate, the mind-body problem, which Barry and I, in our book that just appeared about AI, we have a chapter about this where we argue also from a materialist perspective. But there's a huge body of literature, and it was extremely fashionable in the 70s and 80s and 90s. I think it was one of the first big topics that when analytical philosophy thought was done with language. So then it took on the mind-body problem. So there's thousands and thousands of pages about this, but that's the answer of a physicist. Anything else?
So you should say that although we deal with meaning and so forth as parts of material reality like everything else, that doesn't mean that we reduce them. So we believe that meanings exist. It's just that if we had enough power, we could work out what the underlying physical parts of those meaning experiences are. But since they're different in every person, and since it's very difficult to get imaging information about the physics of your brain, we will almost certainly never know precisely what the material parts of the consciousness of meaning are.
I think the problem is just that the system's too complex. It's not only not about being able to measure it, it's too complex to model it in terms of physics, but it is that's the answer. Now, so what is a theory in physics? So this year, what is nice about classical physics is that the entire classical physics fits on one page, and this is from Feynman. So if you're really serious, you want to do philosophy of physics. So what I did, Tom told me a little while ago that I should study more physics, and which I did. So I worked myself through the 3 volumes of Feynman's lectures on physics. It's a great experience, and in volume 2, at the middle of volume 2, he's showing this table, classical physics at a glance. So this is a theory. Right? This is a typical theory. And what is a theory? It's a coherent totality of propositions formulated with the aim of describing theoretical concepts. So these are entities from mathematics and physics. So a typical entity of mathematics is, for example, the symbol here is called the curl. That's a recipe for creating partial derivatives. That's a mathematical entity, and that's the electric field. That's an entity from physics, a magnitude, a vector magnitude actually. And then we have axioms. These are principles, and hypotheses derived from them. And certainly, most of all, we have a lot of axioms. We do not have axioms in mathematics. So mathematics is an a priori science, so it rests solely on axioms. Then the second, we have models of systems. So we pick a system that we want to model with a theory, and we have models of systems consisting of propositions, which are very often, as we see here, formulated as equations, and possibly also often geometric figures which mediate between the hypothesis and the observed reality. Here, for example, these equations, the first four equations here, these are Maxwell's equations, and they form together the theory of electromagnetism. Here you have the law of motion, which is Newton's law. This is Einstein's modification, the relativistic special theory of relativity modification of it, of Newton's law of motion, which is mechanics. And then we have gravitation, which is a very important force. This is the most important force in the classical mechanics. And so this is another theory that's the classical mechanics theory. And so the third ingredient of a theory is an example of successful model applications, or examples of successful model applications to observations. So these first two things are Carnap's view of theory. So Carnap believes these are the two ingredients. We've modified it a bit, but we add the third one, which is that basically we need successful model applications in physics. At least. This is the theory of physics. Therefore, in my eyes, quantum gravitation theory or string theory are not theories in the sense, there may be pre-theories or whatever, but they're not theories in the sense of physics. So you always need experiments or observations that support and that link your theory to reality. Otherwise, if you don't want to do this, then you can go to the humanities, do gender studies or whatever. Then you don't need any link to reality. But if you want to do physics, you need to have a link to reality. So, any questions regarding this?
Just out of curiosity, is there a reason that we don't have any thermodynamics there?
Yeah. So basically, Feynman would answer that everything in classical physics can be derived from these equations. So you can also derive them. So when you can take this and then you can derive thermodynamics. But yes, of course, thermodynamics deserves. But it even writes this. I think it's chapter 17 or chapter 16 of the second book. And if you read the first book, the first volume of his lectures, then you find he develops very well. He goes almost not historically, but he just says, now we've learned mechanics, now let's develop thermodynamics, and he develops it completely from classical mechanics. So that's why it's not shown here.
Okay.
But there's no heat anywhere.
Yeah, but
so he has to add extra axiom.
There's no energy either. So
what?
There's no energy.
Well,
wait.
Of course, there's energy. Here's
Oh, sorry.
Here's energy. Yeah. So
That's electrical
heat is
field.
just a form of energy. So I mean, this is just it's basically, this table is a bit a joke, but it's a good joke, and so I showed it. Also, it's neat because it allows me to illustrate what this theory is. Yeah, but of course, heat is a form of energy. Okay, so if we move on, so now it gets interesting. So, what are models in physics? So usually you have when you read a physics textbook, you have an idealized textual
special
description
connection for the computer
of an aspect of a system that removes details or properties that prevent the usage of mathematical equations. That's very, very important. So basically always you need some abstraction approximation or something of this kind that enables you to later on use mathematics to describe a certain system. And so the description usually comprises the magnitudes used. Very often it says, let's imagine this and this would be such and such. We know it derives a bit from reality, but it's a good enough approximation and so on. And then the description comprises the magnitudes used to model the system, and often the graphic and also geometric representation. So here you see, for example, the weight on a spring, and you see it is which is often idealized as a harmonic oscillator. And here you see that is the typical graphical system description. Yeah, you all had this at school, if you remember. And then you have a geometric description. So this is, for example, the harmonic oscillator shown as circular motion. And this is now, we'll see this again later so you can understand it a bit better. But this is then now actually a geometric system. And this is important because then the equations usually are written down to relate to the geometric system description. And then we have the second part of the model is the mathematical equations which describes the relationship between the entities. And this formal part of the model sets the physical magnitudes in the context of equations in which they are represented by mathematical variables. So each magnitude of physics obtains, so for example here you have force, and here you have momentum, and the derivative of momentum by time, which is mass times acceleration, gives force. And so each of these variables represents an entity, a magnitude. And well, at least most of them. I mean, in quantum field theory, you have then also variables that point to nothing, but that are there to. Also, actually, in quantum mechanics, we have this. We'll see this later. That's basically the mathematics models the physical reality in an idealized form, and this is how the models look. And now, what are they used for? So they are used. First of all, they are seen as useful to describe, explain, and predict natural and technical processes. Second, the predictive power of physics is seen as a foundation and goal of their science by physicists as well as those using the science, engineers and chemists, right? Everybody thinks that the predictive power is really the core of what makes physics so attractive, and that's also how it is, the fact that how our whole world in which we live now is very much dominated by technical entities, and they are all based on the predictive power of physics. The third aspect is that experimental validation and technical usage of results of physics within itself and for engineering purposes are seen as crucial. So physics uses a lot of machines itself, right? And so this is crucial, but also engineering, of course. And but since World War II, we have a movement in physics, which I now call New School, which has slowly distanced itself from this traditional view of physics and has created a pure physics that separates itself from observation and experiments. What this means, so in the old school, we have no non-local effects. All effects are local. That's Einstein's view, and he says, of course, that how can there be non-local effects? Because we have the light is so the fastest movement that we have is the speed of light, and if we would have non-local effects, then something could move faster than the speed of light. So we cannot have non-local effects. Something that is now heavily debated in quantum physics, and we'll get back to this. But Einstein was right, I think, and he defended his view until he died, and I think he was right, though I think now we have a better view of why he was right than himself, but I think he was right. But modern school says there's non-locality. Then separability, so that the view that the system can be split into subsystems that together determine the whole. But today in the new school, it said that we have inseparable systems like we see in quantum entanglement, which we will get back to later. Then unity, there is only one true state of the system at one time. And non-unity says that states differ at the same time. It's also a problem with quantum mechanics. And then every physicist, and this is still, most physicists would say that every physical model needs to be coupled to experience, whereas there are now in the new school physicists who say we can deduce theories mathematically in physics without experience. These are the string theory proposals. So this is, you see but this is basically the good old physics, quote unquote, on which all our technology rests. Good. So what is physics then? This is a very, very important paper to which Barry pointed me, which was written in 1982 by Robin Horton, an anthropologist. It's called Tradition and Modernity Revisited, and was reprinted in Rationality and Relativism. And it's a 50-page, 60-page paper, so it's like a short booklet. It is a very, very important paper, also to understand what's going on in the humanities. And he from observing primitive societies, as an anthropologist, he has deduced this differentiation or distinguishes primary and secondary theory. Primary theory is the basic knowledge about the life world that enables human beings to survive. So I know that I have to make a step here, that I cannot here, because of this elevation, there's a discontinuity here. I know that I shouldn't drink something, water that stinks, that I can't walk on water, that I can burn myself on hot fire, that there's a day-night rhythm, and so on and so on. So primary theory tells us how to deal with the world and its close related to the common sense in our culture, right? So this is the everyman's theory. And why do we need it? Because we are not anymore like animals, instinct-driven. So we have a lot of our behavior is we can decide ourselves of what we do, and so we need the primary theory to survive. And secondary theory is a theory which explains the world and basically it is on top of primary theory. So all human beings to survive have this primary theory. And if you are as an individual not anymore able to use primary theory, like if you have deep psychosis, or if you have dementia and you do not have people who help you, then you will basically fail. So primary theory is critical for survival. Secondary theory is humans have always asked, why is this so? And this why is this so, secondary theory. And so the oldest forms we know is totemism, for example, polytheism and monotheism. And then philosophy, of course, is also secondary theory, and quantum mechanics is also a secondary theory. However, physics is a secondary theory of world understanding that evolved in accordance and compatibility with common sense and primary theory. So this is very interesting. So from Newton to Einstein, Einstein was a very fierce proponent of common sense and primary. So one of his last texts he wrote is a preface to a book which was printed in the 50s about the view of space in modern physics. And then he wrote the brief and forward, and in this he expresses this, that once more that his total view of physics is very much anchored in common sense. And so general theory of relativity is really a common, although the mathematics in it you need to are complicated to understand, you need to go through quite a lot of mathematical education to understand them. It is very much compatible with common sense still. But Lagrange invented a rigorous mathematical formulation of classical physics in the late 18th century, and since then, physics slowly diverged from common sense. So we will see that in many areas today, physics is detached from common sense and the primary theory, and it has even in some areas abandoned the link to reality. And so this is the evolution of physics in the last 100 years, and we will see more of this during this course, but now we begin with classical mechanics, where we still have a very good link to common sense. So any questions on this before I continue? Yes?
Yeah, I wonder what is the precise relationship between the primary theory and the secondary theory? Is the secondary theory must be built on the primary theory, or can a secondary theory refute a primary theory? It seems to me just like primary theory is just another name for common sense.
Yeah. So of course, secondary theory can totally refute primary theory. I mean, look at the famous. I always forgot the sect, the suicide sect. In the 70s, 1,000 people suicided themselves because their master, the boss of the sect, said that they should now drink this Kool-Aid poison that would bring them into a new dimension of life or something like this. So secondary theories can be, or look at the Nazi ideology, or so secondary theory can be totally destructive and can overrule primary theory, right? So, but in stable societies, and so this was Max Scheler calls the reign of nominalism. Yeah, so if ideas become stronger than reality, then Max Scheler says you always have difficult times. Yeah, here's a good fragment by him about where he describes Max Weber as a very important, one of the founders of modern sociology, where he describes him as a nominalist, and then goes on to discuss nominalism, how dangerous this is. I think we also live now in a time of nominalism again, and so then secondary theory can become stronger, and ultimately it can become so strong that the survival of populations is endangered. Yeah, but normally in good and quote-unquote good time, secondary theory is in kind of a harmony with primary theory, but it can arbitrarily deviate.
I see. So
Can you define nominalism?
Oh, so in the sense of Scheler, it is the view that the world is determined by what we think. So we have, that we can formulate propositions and they determine reality. That's the most extreme form of nominalism, right? That's how Scheler sees it.
I'm not going to say Kant.
Kant is not a nominalist at all. He's a die-hard realist, Barry. Sorry, he's not a nominalist at all. And this is very easy to show. So he has other very big weaknesses, I would agree, but not that he's a nominalist. Now let's start with classical mechanics and the principle of least action. So classical mechanics describes the rotational momentum of bodies moving in space. It was physics as a science of motion. And we will look at a bit of this now so that you get the context of quantum mechanics. So first of all, we have energy of motion, which is you asked me to point with the mouse, Barry, right? Oh God.
I have a I have a laser pointer if you want.
So here this is kinetic energy, and it's defined as 1/2 mass times velocity squared, and because I think I don't need thinking. And because momentum is mass times velocity, if you now divide this equation by m, you obtain velocity equal to p divided by m. If you square this, you can replace the v squared by p squared divided by m squared, and then the m cancels, one of the m's cancels out, and then you get p squared divided by 2m, which is Hamiltonian representation of kinetic energy. And the other energy that is important is the potential energy. So this pencil has a potential energy because it has distance from this level. And if I let it fall down, it takes a different object to let it fall down. So if I let this fall down, then its potential energy will decrease, but its kinetic energy will increase while it's falling. And so therefore, in mechanics, always potential and kinetic energy, the sum of the two is always unchanged in motion. And if you have a field of conservative forces, then it remains unchanged. And oh, by the way, when this hits the ground here, then things are different because then kinetic energy is transformed, dissipated, and but that's a different topic. But basically, the force of motion in the field is this is F. F is equals mass times acceleration. So this is the distance. The double derivative of distance is acceleration. So this is, physicists often put dots on top of variables to show their derivative. If it's clear what it's derived by, so this is derived by time, and so then because they know this, they can put the dots, and this is equals minus the change in the potential energy. And this is just Newton's second law, which you all have learned at school. And so the work done to move from 1 to 2 does not depend on the line, but on the difference of potential between the 2 points. That's another way of saying this. So this is a very simplified view of classical mechanics, and conservation of energy. Here's a small proof of conservation of energy. I don't think we have to go through it. This is just the equation I just showed that relates force to the differential of potential energy. And now you can, if you integrate this, you can show and then go through these reformulations through these algebraic operations shown here. Then you can show that the difference, if you have now 2 time points, right, that the difference of kinetic energy is equal to the difference of potential energy. And that if now you change, if you make a small algebraic operation again, so you put the V2 here, the T1 here, you see that the sum of the kinetic and potential energy over time is conserved. And so that means that energy, and because we know that E equals kinetic plus potential energy, this is E1 and this is E2, and so therefore we get E1 equals E2, and that means that the energy is conserved. So this is a very abbreviated way of showing you this law of the conservation of energy, and this is a very important result of classical mechanics. And then here is another important aspect of classical mechanics. The figures actually taken from your paper, Tom, including your adaptations, but it was you adapted it, I think, from Wikipedia.
Yes, too, from the internet.
And I took it from you, but I'm quoting you here. So. And it is basically so. Lagrange and Hamilton reformulated classical mechanics in the 18th and 19th century, and you see here that and I'm just introducing this. So Hamilton defined a function of distance, and he called distance q and momentum p as it was classical. So this is a position of a particle, this is momentum, and this is a function of the two, and it is an energy function, because this here is a kinetic energy, that's a potential energy. And so if you add them together, you obtain an energy function. And I introduce this now because later on, we will see the Hamiltonian in quantum mechanics, and it will also describe energy. So the only reason why I'm showing this to you is not that you should learn Hamiltonian mechanics, but that you hear this name once, and that you see, then you can recognize it later on again. And so now you can reformulate the laws of motion with the Hamiltonian. So if you make the derivative of a position, which is by time, which is this, then you obtain, if you apply this to the Hamiltonian, you apply here. I was too lazy to recreate the equation. I should not use the calligraphic H. This is the calligraphic H. Later on it will be used for the Hilbert space, so I apologize for this. I didn't have enough time to change this equation. Others I've done, but here you see the right way to write it. This is wrong, but it doesn't matter. So this is basically says that if you make the partial derivative of the Hamiltonian by momentum, then you obtain the position, and vice versa. So if you want to obtain the derivative of the momentum, then which is force, then you have to have the derivative of the Hamiltonian by position. And when you see this d, this means partial derivative. Why is this partial? Because the function takes two variables, and here I only do a derivation by one variable, so it's a partial derivative. And this is for k particles, right? So, but each particle is seen individually. So this is only true if the particles don't influence each other. If the particles influence, if there are many particles influencing each other, it gets very complicated. And so the Hamiltonian function uses energy to define a world line of the particle in space-time. It also has a relativistic expression, and the world line, it's very important. This world line here, you see, this pendulum is moving. It's a very simple system. It's moving at an angle theta. Basically, this angle theta indicates its position. We have time, so it's changing its position over time. And you can see here, for example, when it's here, it's this point, and when it's going back, swinging back, it's this point. The orange point is here, and the red point is there. So these are the extremes of this movement. And if there's no friction, this will go on forever and will be a sinusoidal curve. And when you project this onto a state space, which is a coordinate system where you have the position on the abscissa and the velocity on the ordinate, you can draw the trajectory as a circle. It's a circle we saw a bit earlier. Or you can also plot the position against the momentum, and then you can see here again the points, right? So on the green point you have theta 0. When it swings back on the blue point, theta is 0. When it's here, you have theta is maximal, and when it's red, theta is minimal, and so on. So you can basically see from this picture how you can use how the phase space and state space describes the motion in space. And the Hamiltonian world is deterministic. It's time reversible, given position and momentum. If we have one or a few particles, so then you can use this, and then you can say once I've measured the position and momentum of the particle, and if I have only conservative forces, I can forever calculate the trajectory of the particle, right? And a good approximation is that of this is what's going is the motion of the planets around the sun, for example. Okay, so this is basically a simple view of classical mechanics. Any comments?
Well, yeah, so my question is, so earlier you said that the phase space or the state space are kind of models, but you seem to be committed to say that, so those equations are true in virtue of certain vectors and certain manifolds, right?
Yeah.
So if you think, so as I think that, well, I don't understand, so do you think that the phase space is real, or do you
No.
think it's a model?
I think it's model. I mean, maybe I was not expressing myself precisely, but I think these are models of reality. And in reality, we have behavior of entities, of particles or bodies in space, which are modeled with this phase space. But I don't think that it's a mathematical model of reality, it's not the reality. So this is very important.
Is classical.
No.
But then just suppose, so would you believe that, so if the world was classical, would the phase space be real?
No. So if the world, let's say the world is classical for now, then I would not say the phase space is real, but the phase space is a good approximation, is a model of reality, so it's a good approximation. But if you look at the three-body problem, you already see that you get problems if the three bodies are in a gravitational field. Already you get differential equations that you can't analytically solve anymore. Yes, you can numerically, yes, it's your turn, numerically resolve, but you get the more bodies you get, the more complicated it gets. And then, even if these equations are valid in principle for a few bodies, you can't predict the behavior of the bodies anymore. So I think they are only approximative models of reality. They are not reality, and therefore I think that the ontology of physics and the ontology of mathematics are separate. So physics is using mathematics, but the ontology of mathematics and the ontology of physics are, and therefore I also think that the quantum field theory is not reality, but it's just a model.
So doesn't just say that, so the phase space or whatever geometric structure there is may just be too complicated in order to kind of put it into symbols. So that if we are just not smart enough to kind of compute this.
Yes. So this is the position. If you do not have this position, you become a Kantian in a bad sense. Then you say that there's a noumenon. Yeah. Because then you would say, oh, we can never know how reality is in principle. Yeah. But I think your position is right that the mathematical models are inadequate only because, as you expressed, we are not smart enough. But I would say because our modeling abilities are surpassed by the complexity of reality. However, there are situations in which our modeling capabilities are really excellent, and so where we get very close with the models to reality. However, we can't say in general that we can model reality perfectly with mathematics. But that is not to say that we are not capable of perceiving things as they are. It's just that when it comes to quantifying reality, we have limited capabilities. But I'm not a proponent of the noumenon. So you ask the next question.
Looking at the last sentence, physics cannot deal with the interaction of many particles, and I'm trying to figure out what you mean by physics. That sounds like physics is a mind thing. Is that what your position is?
The mind thing? Physics is a science.
Physics is a science.
Yeah, I'm not saying.
So it's a human thing. It's not a world thing.
Yeah, I mean,
Because the world can deal with anything.
Yeah. So yes. So exactly. So without human beings, there would not be physics. There would be physical reality, right? But physics, I mean, it's a mind-dependent phenomenon that only humans can do, and so the physical reality would be, to a large extent, I mean, the physical reality, at least of the universe, would be completely unchanged without humans, and physical reality, physical processes would go on. But physics is, of course, a human creation, and it's quite a recent one. I mean, in the modern sense, it's only 350 years old. It's only, I think physics, the first physics was really done by Newton and Leibniz. Even Kepler didn't do physics yet in the modern sense. And so yes, That's the answer. It's my answer. Yes?
Would you mathematically distinguish state space and phase space?
Yeah, of course. You see here that in the state space, in this example, the state space has ordinate velocity, and here you have the derivative of is momentum. And so the phase space is the most general description of the movement of the particle, and it's a phase space that Hamilton uses also, because he's using momentum and not velocity. Okay, so now this is lecture number 19 in Feynman's Lectures on Physics, Volume 2, the principle of least action. It's funny because unlike the other lectures, this lecture has not been redacted. So there is a passage where he later on we get to this in a bit, where he wants to show how the Newtonian equation can be derived from the principle of least action. And for this you need calculus of variations, which is mathematically relatively demanding. And then he's saying, so now let's see how we can get this control of this darn thing. He's talking about the equation. It's quite funny. He was very full of humor, this man. Anyhow, so if you look at a particle, and these are drawings made by Feynman during the lecture. If you look at a particle, this is the first time when I'm throwing a stone, and then after a certain time it's here. So this is how it moves, right? And then he says, but we could imagine such a motion, but it doesn't happen. It's always following this pattern of motion. And so that's because the average kinetic energy less the average potential energy is as small as possible for the path of an object going from one point to another. And so the Lagrange function, also called the Lagrangian of a particle with mass m that moves with potential v, is the difference between the kinetic and potential energy. So that's very similar to the Hamiltonian formulation we saw above. Basically, the Hamiltonian formulation is based on the Lagrangian formulation. And so the principle of these actions says that for each trajectory, and now that's a world line, a line in space, which a particle traverses, it has the action equation. So this is an action equation which is an integral over the kinetic energy minus the potential energy, and that's a product of energy and time, yeah, because it's integrating with t. And for this action, the first variation is always 0. And that's the principle of the action. That means that the particle takes a trajectory with a stationary action. And for classic motion, then you can derive from this, you can ultimately derive Newton's second law. And you can see here, it's nicely shown. So when you throw the stone, at the beginning it has a lot of kinetic energy. So it's the opposite of what I showed you. When I drop something, it has a lot of potential energy. At the end, it has no potential energy. And here, actually, the kinetic energy, it has a lot of kinetic energy. Then the kinetic energy decreases, but at the same time, it requires potential energy. And here, then, at the peak, it starts to lose potential energy again and acquires kinetic energy. And this means that, and mathematically speaking, this means that the variation of this integral is zero. And this is a very, very important principle of physics. And as I said, Planck and Feynman were very fascinated by it. And they said, oh, it's such a mystery. So Feynman writes that even in quantum mechanics, the particle sniffs out the right way to move, and so on. It created a lot of excitement. We will get back to this, but it's mainly I show this to you to introduce you to the notion of energy, to show you the Hamiltonian, and to give you a view of how physics was before the big revolution with quantum mechanics happened. Okay, so this was, actually we are faster than I thought. What time is it?
It's 10 o'clock.
10.
We have a break in 15 minutes.
In how many minutes?
In 15 minutes.
Okay, very good. So then I can still start the introduction to quantum mechanics. So first of all, so this is a long chapter. But now we do the motivation, and then we start with the basics of quantum mechanics. So the motivation is the following. So in 1869, Maxwell recognized that classical physics could not explain the specific heat ratio of gases. That was a real problem. But then more problems arose. So this is here a blacksmith holding a piece of iron that he has heated, and you can see this is the part that is not so hot, that looks black. Then here it starts to red. It's hotter, hotter, and hotter until it is white. So it emits the piece of metal, a piece of iron, emits light. And that's called black body radiation. It's a very classical phenomenon. You can see it yourself. If you heat up a piece of metal yourself, then you can see this phenomenon macroscopically. And so the blacksmiths use the color to judge the temperature. So then they beat on a certain part of the metal to form it, and they then know how much force to put on it depending on the glow. And so this black body radiation has this spectrum. So you see here, this is the light spectrum. We will get back to the light spectrum in a bit, but this is short wavelengths, and this is long wavelengths. So it's an inverted scale, and you see that this light. So there's some, when you heat up the metal at a certain energy. So this is the intensity of radiation, independent of the energy. The wavelength is a measure of the energy. And if you heat it up, you see that there's a bit of radio frequency and a bit of infrared frequency coming out. So today you could also say mobile phone frequency, which is also here, right? So that's something you now know better than the radio. The infrared frequency, here there's also microwave, infrared, then visible, and then there's visible. That's what you see, what the blacksmith sees when he looks at the iron. Then you have also some UV light. But then there's no X-rays, so at very short wavelengths there's nothing. So this is a black body spectrum that was measured in the end of the 19th century, and we just saw the peak of the spectrum, and I just wanted to show it to you. And the cause of the radiation is the oscillation of the electrons. So basically, when you heat up a metal, the electrons pick up energy. They get into a high energy state, and then they also fall back to a lower energy state within the atom. And when they do this, a photon gets emitted. And this emission of photons is what creates the light and the radiation you see. And the classical theory to describe this experimentally measured results completely failed. So this is the classical Rayleigh-Jeans law. And you see that the Rayleigh-Jeans law, so these are two different frequencies here. This is lower frequency, lower energy, and higher energy. But it doesn't matter. So you see that at these energies, these are also temperatures, by the way, right? This is a T0 and this is twice T0. At these temperatures, the law is quite good to model the first part of the curve, right? This part of the curve is modeled really well with the Rayleigh-Jeans law, but the Rayleigh-Jeans law then believes that, or models that the radiation increases indefinitely, always more and more and more, as wavelengths get shorter, but that's not what we observe in reality. And that was a big problem for physics. And for quite many years, 15 years, people were staring at this. And here you have the Boltzmann law is plugged into this equation. It looks rock solid from thermodynamics perspective. Nobody knew why this doesn't work. So, and this is, U is here, it's a spectral radiance in the interval that is described here. Nu to the nu, c is the speed of light, k is the Boltzmann constant, t is the temperature, and nu is the frequency. Yeah, while here omega is the frequency. I'm sorry for this. I was mixing up two textbooks, but it doesn't matter because this picture from Feynman is nicer than the one on Wikipedia. That's why I put it in. But you have to imagine that this is omega here, and then it describes how the electromagnetic radiation from a black body depends on its temperature. And the equation failed to describe the radiation at low wavelengths, high frequencies. And now Planck, in 1900, Planck found out that we have to assume a non-continuous, what he called quantized emission of radiation, governed by multiples of a new constant h, the Planck constant. And so
H.
Sorry, H. When I learned mathematics in German, so I always tend to speak in German when I describe mathematical equations. So when you take this and modify this equation with this new denominator with the exponential function, where you have this h here, you still have the expression kt, but it's now in the denominator of the exponent of the exponential function. If you do this, and then you get the results that Planck calculated and that correspond perfectly to what gets measured, almost perfect. And so, but that means that the Lysiad is a discrete number. And that was totally astonishing. Yeah? So Planck himself was suffering physically. Ich leide wie ein Hund, he was writing, I'm suffering like a dog, that because how can anything in nature be quantized? He didn't want to accept it himself. But he was a good, I mean, look at him. He was such a very typical German scientist. Yeah, I mean, you can't look more German than him, I think. Yeah, look at him. I mean, here he is, right? He's such a Wilhelminian guy, you know. He was thorough and reliable, and he didn't try to. He was not a nominalist. He didn't want to adapt reality to what he was thinking, but he wanted to think what reality is. And so, and then he basically said, no, this is the right solution, and it was proven by the experiment. And so the electrons that oscillate under the heat yield the radiation in a quantized fashion. Why is the curve still? Looks the curve, why aren't there any pieces in the curve? Why is it still continuous? Because there are so many other variables, and so therefore you still get a continuous spectrum, but you have to assume that the electrons emit in a quantized fashion. What does quantized mean? So basically you see here the energy levels of an atomic nucleus, right? And they are just multiples of this Planck constant. So quantization means that the energy levels of quantum particles are discrete. And that's the quantum in quantum mechanics. So when you hear quantum in quantum mechanics, it always has to do with quantized energy levels or something quantized. Yeah? That is not continuous but discrete. So if you suppose that the permitted energy levels of a harmonic oscillator, so that's something like this pendulum that we saw, were equally spaced at this is the Planck constant divided by 2 pi multiplied by the wavelengths. If they are equally spaced at this magnitude apart, then the oscillator could take on only these different energy levels. So it can only take these energy levels. And Planck showed that the probability of that's something wrong here. I need to fix this. So Planck showed that the probability of occupying a level of energy E that's the probability, it's alpha multiplied by the exponential of minus E divided by KT. And now suppose that we have it here you see the different, this is now applied to different energy levels of the harmonic oscillator. If you now suppose that we have a lot of oscillators and each is vibrating is a vibrator of this frequency, some of these vibrators will be in the bottom quantum state and some will be in the next one and so forth. And so that's not a mistake. Let me correct it now so that when I send you the presentation it will be corrected. So some of these vibrators will be at this level, some will be here, and so on and so on. And what we would like to know is the average energy of all these oscillators. And if we calculate the energy, we give this equation and get this equation, and that leads then to the equation that we saw on the previous slide. And that was the reasoning through which Planck had to go to find this revolutionary equation for the black body radiation. And this was the first time. It still took more than 20 years to get to the Schrödinger equation in physics. So, but it was the first time that somebody recognized that energy levels are quantized. And it was a huge revolution and created quite a big fuss.
So, you've heard of p-hacking. Is there anything which could be described as an analog of p-hacking? Go back to the previous slide. In Planck's move to that equation there.
What's p-hacking?
P-hacking is where you have a certain body of data which you want to understand, and so you try at random thousands and thousands of different combinations of equation terms until you find one that predicts your data.
Planck, I mean, it is what people do when they so. First of all, Planck saw this experimental data. Then he looked at other examples from mathematics, and it's known that you can use the exponential function to model such distributions. Yeah? So Gauss was the first to show it. And so even Euler showed it in a way, by showing the relationship between the sinus curve and the exponential function. So basically, he knew that he needs an exponential term, then he would probably plug it in and test it out, and then realizing that the right data will not come out if he continues to use not continuous values in this exponential. And so then he said, oh, what happens if I take discrete levels? And then he saw that there are even multiples of always the same. That there must be multiples of always the same basic constant. And that's not p-hacking, that's just typical. This is actually one of the best examples of inductive reasoning in physics. So you have observations, and now you need to find a mathematical model that you handcraft this model, right? That gives you the result. And could you do this today with neural networks? If you set up the neural network input-output, probably yes. Yeah, so it has been shown for many equations of physics that they can be reproduced by neural networks. But it doesn't mean that the machines are. That's not global. But basically, what he didn't do p-hacking. What he did was thinking, what is the mathematical way of getting to this curve? And so that's how he found it. And then he was himself, because he was a good mathematician, he found it, but he was himself shocked by this finding, because he didn't want to accept that anything in nature is discrete. So this is the story how it happened. And this brings us to the break, and we can think of more. Oh no, we have still time for questions. Any other questions?
So you can just finish the sentence about whether an AI could have discovered Planck's equation.
So on its own, of course not. So what you need to do, you need to give the AI as output, you need to give the AI the measurement results, and as input, you need to give it, so to speak, elements of the equation that it can combine and test, and then it can parameterize these elements.
Okay.
And then it will, by minimizing the loss function, it will then get something similar to this.
Okay. But Planck didn't operate like that.
No, he didn't try out at all. He thought systematically first, how can I bend down this darn thing? Yeah, as Feynman expresses itself. And that's how really you feel when you look at, how can I now get an equation that bends down this curve? Yeah, and that's how he put in the exponential, and then he thought, what must be in this part of the exponential, in the
Numerator.
exponential part. So it's here, what must be in there to so that I can get to the value. And then he tried something out, and then he realized that it's quantized, and then he realized that it's even a constant that you can multiply to get to the different energy levels. So that's how it happened, and it's very interesting to read his notes about how he suffered from this insight. He even says, I wish I was wrong, and so on. It's kind of very interesting. Okay, so how long is the break?
15 minutes. Actually 18.